Good day, everyone. Welcome to our meteorology class. And for today's lecture, our first topic is about the Earth's atmosphere. And we have four different subtopics to tackle. First is the Earth as a system, and we will check the overview of the Earth's atmosphere. And then we will also discuss the vertical structure of the atmosphere. And after that, we will check the definition of what meteorology is, including the weather and climate, and as well as the atmospheric hazards that weather and climate can impose to the Earth. And this lecture, I use two different books. You can check out The Atmosphere, an Introduction to Meteorology book by Lutgens et al. And also the second book that I use is The Essentials of Meteorology, an Invitation to the Atmosphere by Ahrens. So if you want to completely follow every details of the lecture, you can check out the first chapter of this book. So the Earth as a system, you can see in this picture, the Earth is in the center, and you can see the four different spheres that encircles the Earth. The atmosphere, biosphere, lithosphere, and the hygrosphere. And this is because our planet is a dynamic body with many separate but highly interactive parts that we call spheres. So these spheres are not isolated. They may be separate, but they are not isolated from each other. That means they are related in many ways to the others. And they produce a complex and continuously interacting whole that we now call and recognize as the Earth system. And the first sphere that we know is the atmosphere, which is the gaseous envelope. This is a life-giving gaseous envelope because if, like the moon, the Earth had no atmosphere, our planet would not only be lifeless, but many of the processes and interactions that make the surface such a dynamic place could not operate. And that's why it's called life-giving gaseous envelope. And next sphere is the hydrosphere. So the water portion of our planet. Hydrosphere is a dynamic mass that is continually on the move. So it evaporates from the ocean to the atmosphere, precipitating to the land and running back to the ocean again. And the global ocean is certainly the most prominent feature of the hydrosphere. This hydrosphere is blanketing nearly 71% of the Earth's surface. So the hydrosphere also includes the fresh water found in clouds, streams, lakes, and glaciers, as well as that found underground. And next of these four spheres is the lithosphere, the Earth's solid outer layer. So the surface of the Earth is called lithosphere. It's very uneven and contains high mountains topography, as well as low areas such as Death Valley, and portions of which lie below sea level. Sometimes the lithosphere is referred to as the geosphere, in which case the scientist includes Earth's mantle and core in its description. So the next that we have here is the biosphere, or the life forms on our planet. The biosphere includes all of the living organisms on Earth, including the vast oceans. Through countless interactions, these life forms help maintain and alter their physical environment. Without life, the makeup and nature of the atmosphere, hydrosphere, and lithosphere would be very different. So by definition, a system is a collection of interacting or interdependent parts that form a complex whole. As you can see in this picture, in this scene, ocean waves is the hydrosphere here that were created by the force of moving air, which is from the atmosphere, that break against a rocky shore, which is the lithosphere. So this shoreline in this picture is one of the obvious example of an interface, a common boundary where different parts of a system interact. And in this next picture, this is obviously the hydrologic cycle. So this process is moving the water from the hydrosphere to the atmosphere and then to the lithosphere, have a profound impact on the physical environment and on the plants and animals, including humans even, that inhabit the affected region. So the parts of the Earth system are linked so that a change in one part can produce changes in any or all of the other parts. And we humans are all part of the complex interacting whole we call the Earth system. So this is the best representation of the interaction of the Earth system. This cycle traces the movements of the water among Earth's 4 spheres. It is one of many subsystems that collectively make up the Earth system. So now, since this is meteorology class, we will obviously focus on the atmosphere. Because when you say meteorology, we are talking about the weather and the energy exchanges that continually occur between the atmosphere and the Earth's surface and between the atmosphere and the space is what produce the effects that we call weather. And in this image, it shows the atmosphere taken from the space shuttle. So the thin streaks called noctilucent clouds are 80 kilometers high, and it is in the dense troposphere that practically all weather phenomena occur. So troposphere is in our Earth's atmosphere, where we will check more in details later. And to give the overview of the Earth's atmosphere, this is a picture of the atmosphere as viewed from the space. The atmosphere is a thin blue region along the edge of the Earth, and 99% of the atmosphere lies actually just within a mere 30 kilometers of the Earth's surface. And the composition of this Earth's atmosphere are different gases. First is the nitrogen gas and the oxygen, and we also have carbon dioxide and water vapor, which is composed of hydrogen and oxygen, as obviously water is composed of that, and other small amount of gases. And to go back, so now going back to the composition of the primitive atmosphere, or what we call the early atmosphere, we have hydrogen, helium, methane, and ammonia. The early atmosphere was composed of these gases, and yet it was recorded to have escaped into space. And then later on, the different gases has formed a much denser layer, which was composed of water vapor, carbon, and nitrogen. So this has consisted of the second atmosphere. And as you can see in this picture, it has been said that the Earth's first enduring atmosphere was formed by a process called outgassing, which is a process that continues until today from hundreds of active volcanoes worldwide. Outgassing is a process through which gases trapped in the Earth's interior are released. So, in this second picture, you can see the erupting volcanoes, same as the first one, and it has sent tons of particles into the atmosphere, along with vast amounts of water vapor, carbon dioxide, and sulfur oxide, which has influenced the components of our atmosphere. And so, what happened is when there was heavy rainfall, this rainfall has carried down the carbon dioxides towards the oceans and deposited these carbon dioxides also in rocks and was made into limestones. Therefore, this carbon dioxide has lowered its content in the atmosphere, and the atmosphere has become nitrogen rich. And also for the water vapors, the sun rays has split these water vapors from hydrogen and oxygen composition, or the water composition. They split separately the hydrogen and oxygen. So given that hydrogen as the lighter molecule, it has risen up and escaped to the space, and therefore leaving oxygen behind. And this oxygen that was left slowly increased the plant growth. And through this plant growth, with the photosynthesis, it produces more and more oxygen. That explains why our atmosphere has oxygen now these days. And to look at the closer composition of the current atmosphere, we have here the biggest component is the nitrogen gas. The nitrogen composes 78% of the total of the atmosphere. And the next to the nitrogen is the oxygen, which is 21% in total. So these two gases, the nitrogen and oxygen, make up about 99% of the volume of clean, dry air. And these two gases are what we call the non-variable components. And these non-variable components are what we call the permanent components, are of little or no importance in affecting the weather phenomena. And this composition has come about because of, for example, the oxygen that was released when I've mentioned in the previous slide that the splitting up of the water vapor, the hydrogen separated from the oxygen, and the hydrogen rose up to the space and the oxygen was left. And this new oxygen released they primarily went to the ocean to have the chemical process in there with the iron, and with that, after the available iron satisfied its need for oxygen for the chemical process, and there are primitive bacteria also, such as the cyanobacteria, that use this oxygen in making food and in photosynthesis. And also this has increased the oxygen generating organisms, and therefore producing more oxygen molecules that were beginning to build up in the atmosphere. And so these oxygen molecules absorb ultraviolet radiation, And when they absorb these ultraviolet radiation, they arrange themselves and form as the ozone. Ozone is also from the oxygen molecules, but instead of having 2 atoms, it has 3 atoms. So when this oxygen with 2 atoms has rearranged and one oxygen with 1 atom could collide with an oxygen molecule with 2 atoms, then they form the ozone with the 3 atom molecule oxygen. And at the surface, the balance between destruction and production of these gases is always keep up. That means, for example, in the nitrogen, there is a process that nitrogen is removed from the atmosphere, and there is a process that nitrogen is put back to the atmosphere. And these processes are primarily by biological biological processes that involve soil bacteria. And example is that the output here, the nitrogen is taken from the air by tiny ocean-dwelling plankton that convert it into nutrients and that help fortify the ocean's food chain. And from this, they also have the input of the nitrogen. That was the reason why there are more and more nitrogen in the air, in the atmosphere, aside from oxygen. The input was through the decaying of plant and animal matter. Then the nitrogen is returned to the atmosphere by that time. So aside from these permanent components or the non-variable components that we've discussed in the nitrogen and oxygen, we also have these variable components. We have the carbon dioxide and the water vapor. So these variable components is said to be significantly affecting the weather and climate. And as you can see in this figure, the main components of the atmospheric carbon dioxide cycle is shown that fuel combustion, volcanic activity, burning of plants, respiration, soil decay, deforestation, and carbon dioxide evaporates. These all goes to the atmosphere. And these are the gray lines that shows the process that put carbon dioxide into the atmosphere. And the red lines, such as the photosynthesis, and when carbon dioxide dissolves towards the marine life, towards the ocean, it shows the process that removed carbon dioxide from the atmosphere, the balance, that the input and the output that it has to make. So this carbon dioxide is an efficient absorber of energy and thus influences the heating of the atmosphere. So carbon dioxide traps a portion of the Earth's outgoing energy. Consequently, with everything else being equal, as the atmospheric concentration of carbon dioxide increases, so should the average global surface air temperature. And in this graph, you can see that since carbon dioxide absorbs energy and traps the heat, then more carbon dioxide, then more the higher temperature. It shows in here the atmospheric temperature. The atmospheric carbon dioxide has been measured at Mauna Observatory in Hawaii since 1958 and until 2020. It has shown that there has been a consistent increase since monitoring began. So this is the zigzag red pattern reflects the seasons during the spring, summer. That's why there's a zigzag. And this black line is the seasonally corrected data. It shows that the monthly concentrations of atmospheric carbon dioxide is increasing. And that means also an increasing in temperature. And aside from the carbon dioxide, we also have the water vapor. Water vapor, or the invisible gas, that varies greatly from place to place and from time to time. So this water vapor is measured through humidity. Humidity, as we always hear, it refers to the amount of water vapor in the air. And it is an important vapor. It is the important gas in our atmosphere because it releases latent heat when changes from one state to another. So going back to the change of state of water from gas to liquid, that means condensation. And from liquid to gas, that means evaporation. So the gas to liquid, the condensation, could be also through precipitation. I'm sure you already are very familiar with these terms. And again, water vapor is an extremely important gas in our atmosphere. Not only does it form into both liquid and solid cloud particles that grow in size and fall to the earth as precipitation, but it also releases large amount of heat. So when water changes from one state to another, it absorbs or releases energy, termed as latent heat. So this latent heat is also termed as hidden heat. That means hidden heat. And like carbon dioxide, this water vapor is a potent greenhouse gas because it strongly absorbs a portion of the Earth's outgoing radiant energy. Somehow, the absorption of this radiant energy, it forms somewhat like a glass of greenhouse that prevents the heat inside from escaping and mixing it with the outside air. So this has a significant role in the Earth's heat energy balance. And this trapping of energy close to the Earth's surface is called the greenhouse effect. So this greenhouse effect keeps the average air temperature near the surface much warmer than it could be otherwise. And we will talk about this greenhouse effect more in detail in the next lecture. Aside from the two non-variable components, so we have another two more variable components, the aerosols and the ozone. So again, they can significantly affect the weather and climate. You can see in this picture, these are the examples of the aerosols. The satellite images that shows two examples of aerosols. In the left side is a large dust storm that is blowing across northern China towards the Korean Peninsula. So in this first arrow, This is the storm of dust. And then the second arrow is a dense haze toward the south bottom center. This is a human-generated pollution. So these are aerosols. And this could consequently show the second photo. In the right, it shows dust in the air that can cause sunsets to be this colorful with the orange color. And so as to say, the definition of aerosols, it's a tiny solid or liquid that are suspended, the particles that are suspended of various composition. And these aerosols act as surface on which water vapor may condense. Then they play a critical function in the formation of clouds and fog. And also, just like the carbon dioxide and water vapor, they absorb or reflect incoming solar radiation. And they contribute to the optical phenomenon we have all observed, as also shown in the second picture in the right. It showed a varied use of red and orange at sunrise and sunset. So these aerosols could originate from many sources, for example, natural and human-made. That includes sea salts from breaking waves for the natural, fine soil blown into the air, the smoke and soot from fires, pollen and microorganisms lifted by the wind, ash and dust from volcanic eruptions, and more. So, thus, when an air pollution episode is occurring, or when ash fills the sky following a volcanic eruption, the amount of sunlight reaching Earth's surface can be measurably reduced. That is the role of the aerosol. That's why it can significantly affect the weather and climate in the long run. The next here, as shown in the picture below, is the Antarctic ozone. You can see in the Antarctic ozone, the color violet is the hole. From 1979 to 2016, the hole has become bigger. So the two satellite images shows ozone distribution in the southern hemisphere on the days in September, when the ozone hole was largest. So these purple and blue colors are where there is the least ozone. The yellow and the reds are where there's more ozone. So ozone actually is a form of oxygen that contains 3 atoms in each molecule. So 1 molecule in 3 atoms. Or rather, 3 atoms in 1 oxygen molecule. And this ozone is concentrated in stratosphere between 10 to 50 kilometers height range, where there is a crucial balance exists. So the ozone accounts for just 3 out of every 10 million molecules. Its distribution is not uniform and is concentrated in the layer called stratosphere. So this between 10 to 50 kilometer height range above the Earth's surface, or is what we call the crucial balance, where it exists. The ultraviolet radiation from the sun is sufficient to produce single atoms of oxygen, and there's enough gas molecules present to bring about the required collision to make this ozone from the 2 atoms molecule of oxygen. One will separate, and then this one will collide to the other two atom molecule, oxygen. And again, it absorbs the sun's ultraviolet radiation. That's why it protects us from the sun rays. However, there is what we call the ozone depletion, as what you can see also in the picture, that there is a hole in the ozone. So this ozone depletion increased the UV radiation's most serious threat to human health. And this is because of the chlorofluorocarbons. Well, not just because of the chlorofluorocarbons, but this is the chemical that is known to be the most significant in offending the ozone layer. And because of that, there was a Montreal Protocol that was developed in 1987 to eliminate the production and use of these chlorofluorocarbons. So a global issue of ozone depletion has become global. So the ozone depletion issue has become global, and although stratospheric ozone is concentrated high above the Earth's surface, it is vulnerable to human activities. So manufactured chemicals break up ozone molecules in the stratosphere, and it weakens our shield against the UV rays. So measurements of the past 3 decades confirm that ozone depletion is occurring worldwide and especially pronounced above Earth's poles. That's why the Montreal Protocol was developed. So now we're coming to the vertical structure of the atmosphere. So for the vertical profile of the atmosphere, it has been said that it can be divided into a series of layers. But first, let us examine the two important variables, the air pressure and the air density. When you say air pressure, it's called atmospheric pressure. It is simply the weight of the air above. And the air density is the number of air molecules in a given space or volume. And so, in this graph, let us examine the changes in atmospheric pressure with height. Obviously, the pressure at higher altitude is less because there is less air, then there are fewer air molecules above the altitudes. In here, you can see the red line in the graph. Going up, it's becoming less and less pressure. And so, a change in air density can bring about a change in air pressure. As you can see in this second figure, both air pressure and air density decreases with height. So as the altitude increases, in the y-axis, it's the altitude in kilometers in the left side. As it increases, the air pressure that is represented in millibars at the bottom of the x-axis, it has become lower as you go up. And so is the air density, both the air density and the pressure. At sea level, you can see that the average pressure is 14.7 pounds per square inch. So this corresponds to a weight this corresponds to the average pressure of 1000 millibars, just slightly more than 1000 millibars. So this graphic portrayal of pressure and the figures show that the rate of pressure decrease is not constant, because if you can see, the decrease is rapid at first from 1000 until around 500. It's very rapid at the altitude of 4 kilometers. And then it slowly decreasing as it goes up. This is because the air pressure, that's why the air pressure falls at the decreasing rate with an increase in altitude. That's because the air is highly compressible, that the gases that make up the air expand with decreasing pressure and become compressed with increasing pressure. So if the atmospheric pressure is simply the weight of the air above, that means the more air molecules, the more weight it has. So the air pressure and air density goes together. If the air pressure goes up, the air density goes up. However, at an increasing altitude, at an increasing height, when there are lesser air density, that means lesser number of air molecules, then it must also have lesser weight. But as you can see, the decline, as you go really up, it has slowly declined. That is because the molecules is highly compressible. That if it has more space, then the air can expand, and if it has more gases, then they could compress. So moving on to the different layers of the vertical profile of the atmosphere, these layers could be divided based on the temperature measurements. So this instrument to measure the temperature in the vertical profile of the atmosphere, it's called radiosonde. So this radiosonde, it's used to measure the actual environment lapse rate, as well as gather information about vertical changes in air pressure, in wind, and humidity. So a radiosonde is an instrument package that is attached to a balloon and transmits data by radio as it ascends through the atmosphere. And so in this graph, in this figure, it shows the 4 different layers of the atmosphere: the troposphere, the stratosphere, the mesosphere, and the thermosphere. So in general, the actual temperature profile can be quite variable from one day to the next, particularly in the lower atmosphere. So the air temperature decreases with increasing height, as you can see, particularly in the lower atmosphere, particularly in the troposphere. So in the x-axis, it represents the temperature, and in the y-axis, it represents the height in kilometers in the left side, and in the right side, it's the height in miles. So as you go up The higher the altitude, the lesser the decreasing temperature it shows. And this rate at which the air temperature decreases with height is what we call the environmental lapse rate. So this lapse rate, or the environmental lapse rate, is not constant, but rather can be highly variable and can vary over the course of a day as a result of fluctuations in weather, as well as seasonally and from place to place. Sometimes shallow layers where temperatures actually increase with height are it's also observed in the troposphere. So this happens. This condition can sometimes happen, which air temperature increase with height is called temperature inversion. And so, to check one by one, we have first is the troposphere, next is the stratosphere, third is the mesosphere, and the last layer is the thermosphere. So for the troposphere, this was termed or coined in 1908 by Tesserent Tibort, and this is from the Greek word tropion, meaning to turn or to change. So this literally means the region where air turns over, and that refers to the appreciable vertical mixing of air in this lowermost zone. So this layer is called the weather sphere, because troposphere is the layer that essentially all important weather phenomena occur. Almost all clouds and certainly all precipitation, as well as all our violent storms, are born in this lowermost layer of the atmosphere. And the thickness of this troposphere is not the same everywhere. And the temperature continues to decrease to an average height of about 12 kilometers until the tropopause, or the last mark or the last level of the troposphere. As you can see that in this red line, this is the fluctuating or the varying temperature. So from the troposphere here down below, it decreases if you go up to the Mount Everest. And the temperature decrease, it continues up until the end of the troposphere, or up until the tropopause. So the next layer after the troposphere is the stratosphere. So this stratosphere, the temperature remains nearly constant, as you can see the red line, until 20 kilometers. It's nearly constant until it reaches the maximum ozone here in the yellow label, the yellow colored in the graph. Then it has a sharp increase until the stratopause. So the rise in temperature is due to ozone. If you remember that the ozone captures the solar energy, that's why the temperature in this region is increasing. And there is a very little vertical mixing, because unlike the troposphere, where there is a vertical mixing, literally, where there's a change, just like its name has where it came from. So the stratosphere is opposite. There is a very little vertical mixing. This is because the stratosphere experiences a temperature inversion, where cold air lies beneath warm air. So this is in contrast to the opposite occurrence in the troposphere. This is because of the ozone layer. And so then the third layer is the mesosphere. So in the mesosphere, the temperature decreases with height until the mesopause. So if in the stratosphere the temperature is going up, in the mesosphere the temperature is decreasing again. And there is abundant vertical mixing, just like in the troposphere. And the average temperature approaches negative 90 degrees. You can see in here that it's the coldest temperature anywhere in the atmosphere. So the mesosphere is one of the least explored regions of the atmosphere. That is because it cannot be reached by the highest flying airplanes and research balloons, nor it is accessible to the lowest orbiting satellites. So it's not possible to explore. That's why it's the least explored region. So next is the thermosphere. So the thermosphere extends outward from the mesopause and has no defined upper limit. So a layer that contains only a tiny fraction of the atmosphere's mass. And the temperature again rise to extremely high values of more than 1000 degrees Celsius. And this temperature is defined in terms of average speed at which molecules move. So that's why the temperature again increases as the oxygen and nitrogen atoms absorb a very short wave, high energy solar radiation. But since the temperature is defined in terms of average speed, it is not comparable to the temperature that we have experienced near the Earth's surface. That means the temperature is depending on the movement of the molecule. The higher the speed, the higher the temperature, because the gases of the thermosphere are moving at a very high speed. That's why the temperature could reach until 1000 degrees Celsius. It's very high. But the gases are so sparse that collectively they possess only an insignificant quantity of thermal energy. So even if it reached at the temperature that high, it does not feel the hotness that we can feel comparable to the surface of the Earth. And so after all the 4 layers of the Earth, of the atmosphere, we have also the ionosphere. Ionosphere is actually called an electrified region within the upper atmosphere. where fairly large concentrations of ions and free electrons exist. So ions are atoms and molecules that have lost or gained one or more electrons. And this is an electrically charged layer located between 80 and 400 kilometers above Earth's surface. So here, molecules of nitrogen and atoms of oxygen are readily ionized as they absorb high-energy shortwave solar radiation. So ionization is a process in which the affected molecule or atom loses one or more electrons and becomes a positively charged ion. And the electrons set free then travel as electric currents. So this is where the region of the ionosphere. And now we come to check the weather and climate definition. Meteorology is basically defined as the scientific study of the atmosphere and the phenomena that we usually refer to as weather. That's why in the previous slides we were talking about the atmosphere and where the weather mostly occurs. So when you say weather, it actually refers to the state of the atmosphere at a given time and place. So now, what is the difference between weather and climate? Weather is constantly changing, sometimes from hour to hour, and at other times from day to day, whereas the climate represents the accumulation of daily and seasonal weather events, the average range of weather over a long period of time. So, changes in the weather are continuous and sometimes seemingly erratic. It is nevertheless possible to arrive at a generalization of these variations. So, such a description of aggregate weather conditions is termed climate. And both of these, weather and climate, is expressed in terms of the same basic properties or elements that are measured regularly. So these elements could detect the weather patterns, and the climate could be depicted through these variables, such as the temperature of the air. The temperature of the air is the degree of hotness or coldness of the air. And another variable is the humidity of the air. This is a measure of the amount of vapor in the air, as what we've mentioned. And the type and the amount of cloudiness is another variable to check. This means a visible mass of tiny water droplets and or ice crystals that are above the Earth's surface. And the next is the type and amount of precipitation. Precipitation is any form of water, either liquid or solid, rain or snow, that falls from clouds and reaches the ground. And then fifth is the pressure exerted by the air. We've mentioned this, that air pressure is the force of the air above an area. And the next variable that is needed is the speed and direction of the wind. So this is the horizontal movement of the air. And the last element that has to be measured regularly in order to detect the weather patterns and climate is the visibility. This is the greatest distance that one can see. And now that we've learned the definitions of weather and climate, as well as meteorology in general, we will check the maps. In these figures, in the left side figure, this is the satellite image taken in visible reflected light, shows a variety of cloud patterns and storms in the Earth's atmosphere. You can see in here, on the left side, there is a middle latitude storm. The middle latitude storm is not a tropical storm. It's not the storm that we can find in our country. And there is also here the thunderstorms and the hurricane. So thunderstorms, that is tall churning clouds accompanied by lightning, thunder, strong gusty winds, and heavy rain. So a tornado is another type of storm or element. A tornado is an intense rotating column of air that usually extends downward from the base of the thunderstorms. So sometimes it's called twisters or cyclones. They may appear as ropes or as large circular cylinder. So as you can see, there is no tornado, but we can see a hurricane. Hurricane is a slightly smaller but more vigorous storm that is located over the Pacific Ocean near the latitude of 12 degrees north and the longitude of 116 degrees west. So you can see here the hurricane, the tropical storm. With its swirling band of rotating clouds and surface winds in excess of 64 knots or 74 miles per hour. This is the hurricane. So the diameter of this hurricane is about 800 kilometers. So this tiny dot at its center is called the eye. So near the surface, in the eye, winds are light, skies are generally clear, and the atmospheric pressure is lowest. And as you can see in the next picture, in the right side, this is the simplified surface weather map that correlates with satellite image. And we have this key, which represents the cold front in blue, inverted triangles, and warm front is the red small hills. And we also have stationary front, occluded front, thunderstorm, light rain, rain shower, wind direction, and wind speed. So it simply shows that in this map, it shows different, for example, the wind speed, the wind direction rather. So the wind direction from which the wind is blowing is showing. It is given by lines that parallel the wind and extend outward from the center of the station. And the wind speed here, the rate at which air is moving past a stationary observer, is indicated by barbs. You can see by barbs. And the boundary that separates the warm and cool air appears as a heavy colored line on the map, which is a front. Then across which there is a sharp change in temperature and humidity and the wind direction. It simply shows the weather map. What is happening and the atmosphere at space and time. So now that we have seen rather the different maps, and we know what is weather and climate, we've had enough backgrounds of atmosphere. We can also see now the atmospheric hazards that it can bring to the human beings or to the earth. So atmospheric hazards, for example, is the thunderstorm here in the picture that is developing and advancing along an approaching cold front. So thunderstorms or severe storms could cause floods, just like in this picture. Flooding, and this is in Nashville, Tennessee, and it could destroy properties and take away lives of the many. So that's why it's called atmospheric hazards. Some are storm related, such as blizzards or like very strong snowstorm, and this picture is an ice storm or freezing rain. So this is in New York, where the utility poles and the power lines were way down, forcing the road closure. So others are not directly results of storms, such as or cold waves, fog. And in some years, the loss of human life due to bitter cold exceeds that caused by all other weather events combined. So these are just examples. We also have here the lightning. Lightning are sometimes feared because it can cause uh, life and death, and also tornado. And there, in this picture, there is a tornado and a rainbow formed over a south central in Kansas. It looks nice, but after that, the destruction is extensive. So the damage caused by a tornado looks like this and could also look like this, the hurricanes and tornadoes. So these are some of the few atmospheric hazards. More of these is because of the heat waves that could cause wildfires and also causing drought are example of the effects of the excessive heat because of our climate change. And in summary, these are the key points to remember: that the Earth's atmosphere is a mixture of many gases, and both water vapor and carbon dioxide are important greenhouse gases. And ozone in the stratosphere protects life from harmful ultraviolet radiation. And the atmospheric pressure at any levels represent the total mass of air above that level. And the atmospheric pressure, it always decreases with increasing height above the surface. And so, the rate at which the air temperature decreases with height is called the lapse rate or the environmental lapse rate. And a measured increase in air temperature with height is called inversion or temperature inversion. So the atmosphere may be divided into different layers according to its vertical profile of temperature, its gaseous composition, or its electrical properties. But we've seen the vertical profile of temperature. And the troposphere is the layer that essentially all important weather phenomena occur. So that would be all for today. And for the next meeting, I will advise you to read the next chapter of the books that I have previously shown in the slide. So thank you so much and have a nice day.